Okay, in this online lecture, we're going to look at the formation of diols from alkenes. To form a diol, diol means two alcohols. And the type of diol that we're going to be looking at here is what we call vicinal diols. This is called a vicinal diol because the alcohols are in the same vicinity as each other. To make a diol with syn addition, what we actually are going to use is something called osmonium oxide. Once the osmonium oxide adds, then we reduce it with sodium bisulfite. Bisulfite. If I look at this compound, how does this occur? The osmonium oxide, it would be osmonium with two oxygens sticking out. It basically comes and sits down on top of the double bond, and it forms this compound here. You can see there's the osmonium oxide, and these are the bonds that it formed. And it used to have a double bond on one of these, and of course the single bond here with the non-bonding pairs. The non-bonding pair on the oxygen reaches out and grabs this carbon, and the double bond reaches up and grabs that oxygen to form this intermediate. We call it an osmate. That osmate then is reduced by sodium bisulfite. The reduction occurs on the osmonium, so the syn oxygens remain in place. So we end up making a cis diol. So what is the product of this reaction? Well, it's going to be a cis diol. These two alcohols these two methyl groups are going to remain in place, and what you are going to end up with is an alcohol group here and an alcohol group here without that double bond. Notice that this is oxidation overall. It's not just the addition of water. That would put hydrogen on one carbon, and that's not a net oxidation. But because you're putting two oxygens on the carbons, you're ending up oxidizing the molecule. This is syn addition. Notice the hydroxyl groups are on the same side, and this is down. The chirality of this one's not being shown, it's just being shown as straight out. And it really could be either down or up, depending on the side of attack of the osmonium oxide. Notice we're following a compound that does the oxidation with something that does reduction. So we get a double oxidation here, and then we get reduction of that. So here is the same conditions, osmonium oxide followed by sodium bisulfite. So what would be the outcome of this reaction? Okay, if I go to figure out the outcome of this reaction, no stereochemistry is going to be involved here. You don't have to worry about syn. It won't show up because this molecule can rotate around the double bond, and this side of the carbon is symmetrical, so you won't find a difference. What's the most important thing that you know here? You put a hydroxyl here, and you put a hydroxyl here, and the double bond goes away. Okay, we're going to look at oxidative cleavage. Oxidative cleavage is going to give a dicarbonyl. Notice we have a carbon-carbon double bond here. We're going to treat it with ozone, which makes this malozonide. It would be where the ozone is added to one side of the double bond, which then rapidly rearranges to give what we call an ozonide. This ozonide then can be reduced with zinc and acid. The zinc and acid cleaves this in half, putting a double bond to an oxygen here and a double bond to an oxygen here. If it turns out that there's a carbon here and a carbon here on this carbon, then that will become a ketone. If it turns out there is a hydrogen in one of these places, any one of these places, that carbon that has a hydrogen on it will result in an aldehyde functional group. To make ozone, what we do is we take oxygen and we run electricity through it and it makes ozone. In older electrical appliances, like vacuum cleaners, before they were made a little bit more with less ability to have an electrical arc in them, you would smell ozone from the running of, let's say, a vacuum cleaner that had a short in it or some other thing like that. Occasionally you will still smell ozone when you have an electrical discharge occurring in some kind of appliance. It has an interesting odor. I can't tell you what it smells like. I just know that when I smell it, I know it's ozone. We can actually use this reaction in helping us to figure out what an unknown compound is. Now, if I look at how we today with our modern techniques, we will use spectroscopy, something we'll learn about later, in order to elucidate the structure of this. But only as long ago as maybe 40 years ago, we used to use these reactions a lot to figure out what is the structure of an unknown compound. This word elucidation means to shine light on. So when we use this reaction to try and figure out the structure of something, we're actually kind of using the results of the reaction to shine light on a structure. So if I take a structure and I react it with ozone and zinc acid, then look at the structures of the products. And so if I did not know what this is, and I end up getting cyclohexanone and acetone, I can deduce by thinking backwards what the compound was. To figure out the product of this reaction, so if I cover up this and I say, what is the product of this reaction, the way I do it is I cut this in half. It's called cleavage. So I cut this in half, and I'm going to put an oxygen on either end of the cut, and I end up getting cyclohexanone and acetone. If I don't know what this is, and I want to figure out what could the production of these products from these reaction conditions, what could it have been, I just take the two compounds, I cut off the oxygens, and I stick the two halves of the double bonds together to create this structure. Okay, notice this side of the double bond has a carbon on either side. So I'm going to make a ketone here. This one's called cyclohexanone. This carbon has a carbon on either side. So it ends up making a ketone, and this one's called acetone. When I look at this molecule down here, when I go to do cleavage, I'm going to cut here and put a double bond to an oxygen on this carbon. Or you can just say you cut this in half and stick an oxygen on either end of the cuts. Then what you get is an aldehyde here or an aldehyde here. And an aldehyde here, not or. And so I can figure out what is the product of this reaction by cutting and sticking on two oxygens. Or if given this, under these conditions, what is the product over here? What do? I cut this off and I cut this off and stick it back together. Notice this is an ester. It is not the product of ozonolysis. You only have aldehydes and ketones that are products of that. So when this reaction, this was not given to you and you were given these reagents and those two products, you just cut off the oxygen and stick the two ends of the double bond together to figure out what is the potassium permanganate can be used to do oxidation, except potassium permanganate is like turning loose a lion in a herd of rabbits. It's just there's going to be a lot of damage done. And what you have is oxidation of the carbon to the ultimate amount. And let's see what we're talking about. Oxidation is the addition of oxygen. So when I did oxidative cleavage here, I cut this in half and just stuck oxygens on it. But if I do oxidation with potassium permanganate, what happens is not only do I cut the double bond in half and stick oxygens on there, I also then take this hydrogen that was attached to that carbon and oxidize it down to this oxygen-hydrogen bonding, and this gets oxidized all the way down to carbon dioxide. So when I use potassium permanganate, I look at the carbons in the double bond. If there's 2 carbons on the carbons in the double bond, you just cut and stick an oxygen on. If there's only 1 carbon on the carbon in the double bond, you cut, stick an oxygen on, and take that hydrogen and turn it into this oxygen-hydrogen bonding. If you have no carbons, so it's like this one right here, there's 2 hydrogens attached to that carbon. What happens is that carbon gets oxidized all the way down to carbon dioxide. So let's look at these examples. If I take this compound and do oxidation all the way down that I can, because these are ketones, I'm just going to do the same thing that ozonolysis did. There's no hydrogens here to oxidize further. If I look at this compound and do oxidation with potassium permanganate, not only am I going to cleave it and put oxygens on the ends of the double bonds, but this hydrogen will be turned into an oxygen-hydrogen, and that hydrogen will be turned into an oxygen-hydrogen, and you end up getting carboxylic acid functional groups on each of these 2 carbons. You see how it's all this and that carbon, and it's a carboxylic acid functional group. All this, that's all this, plus this carbon, which is oxidized down completely to a carboxylic acid. Why is it oxidized down? Because there were hydrogens there. Why are these not oxidized down? Because there's carbons on either side. So this is a picture of how can you figure out how what structure came from these products that were made by ozonolysis followed by zinc and acid. The way that you do that is you just cut this oxygen off, cut that oxygen off, and stick the 2 ends together, and it makes this compound. So what is the outcome of this reaction? Okay, to figure out the outcome of this reaction, you see that it's osmonium oxide with sodium bisulfite. Those conditions make a diol. So what diol will we make? We will take the double bond, and on 1 carbon of the double bond we put 1 alcohol group, and on the other carbon of the double bond we put another alcohol group, and this the second bond of the double bond disappears. So this is the product. So what is the outcome of this reaction? Potassium permanganate with methylene cyclopentane. The outcome of this reaction is that we do cleavage. When we do cleavage, anything that has hydrogens on it gets oxidized down completely. So this carbon has 2 carbons attached, so it only makes a ketone right here. But this carbon, because there's 2 hydrogens attached, it gets oxidized down completely. What is the outcome of this reaction of methylene cyclohexane with ozone followed by zinc acid reduction? The outcome of this is oxidative cleavage, so it gets cut in half. Notice when we cut this in half, we get the carbon here has an oxygen put on the end of that double bond now. And if we cut this side in half, we get a carbon. See, there's 2 hydrogens here. So there's the carbon with the 2 hydrogens from over here. And what happens, this gets cut and an oxygen popped on the end of that double bond. What alkene and reagents would be needed to make this product? Okay, to make this product, you recognize that it was a diol and that it had to come from an alkene. Now, the reagents for the production of a diol is osmonium oxide followed by sodium bisulfite. But the alkene, you have to think, these two have to be adjacent to each other. So in order to get them adjacent to each other so they could have been added syn, you've got to rotate this side around, whoop, and flip this over, okay, and then so that it goes all the way down. That would put the hydrogen on the same side as this part of the molecule. So here are the reagents that we need. That's step number 1, would to make a 1,2 diol or a vicinal diol from these reagents. And then you would have to recognize that the alkene was this. This is a kind of a hard problem, but it's doable, and you'll be able to do this problem more easily in the future as you start practicing these. What alkene would be needed to make this product? Well, if we look at this again, we're going to need the osmonium oxide with the sodium bisulfite. But notice that the hydroxyl groups are already syn to each other. So that means you just put the double bond in without having to do any rotation. And so it is the cis double bond that is needed to give this arrangement. What alkene and reagents would be needed to make these products below? Well, if you look at these two products, you can see they came from some kind of cleavage. If I look, it makes a carboxylic acid here. So I know the reagent. To make a carboxylic acid, you can't use ozone and zinc oxide. What you have to have had was potassium permanganate. The alkene you get by just taking this part and putting it on the end of this double bond. Take the oxygen away and take the methyl and the carbon and stick it on the end there. That must mean there's a hydrogen there too that was oxidized down to this part. Okay, so this is the reagent that we would need in order to get this one. What alkenes would be needed to form these two products from potassium permanganate? Okay, it's very easy to do this one. This one is just 2 ketones, so you know that this was one side of a double bond and this was another side of a double bond. So cut off the oxygens and stick the 2 halves of the double bond together and you get this. Do y'all see this? Watch. 1, 2, 3, 4, 5. Look at this. 1, 2, 3, 4, 5. And see, there's the double bond that these used to be in. You see that attached to that double bond is a methyl group. There it is. Here's a methyl group on that double bond right there. So this is the product of that. This is a product of oxidative cleavage of this alkene. Likewise, if we look at this molecule, you'll see that this is a carboxylic acid. So you know if it was potassium permanganate, this used to be a hydrogen. So again, you count 1, 2, 3, 4, 5, and a double bond between these 2 carbons. So let's put that up there. So there's that double bond between the 2 carbons and the 5 going around. One of them has a methyl group on it. The other one has to have a hydrogen on it because we have potassium permanganate making this. All right, 1,2 diols can be cleaved also. So if I take a syn diol and I treat it with periodic acid, what do I get as the outcome of that? The periodic acid adds to the diol like this, and then it rearranges and cleaves it open to 2 carbonyl groups. The result is, if this had been an alkene, the same result is the outcome as if I did zinc oxide, same result as if I did ozone followed by zinc and acid. So a diol is cleaved by periodic acid to 2 carbonyl groups, which is the same product that you get, 2 carbonyl groups from ozone and zinc acid. If I look at this compound, This is a diol. If I use periodic acid, it cleaves it, and notice cuts this in half and puts a double bond oxygen here and a double bond oxygen there, so I get 2 of these. This would be just the same as if take away these 2 alcohol groups and put a double bond in here, and then I take ozone and zinc oxide and I make this. So to get this from an alkene, I use osmonium oxide. Once I get a diol, I can use periodic acid, and it does oxidative cleavage. 2 different ways to get it. So, what is the product of periodic acid with this diol? Periodic acid is going to cleave it to the carbonyl. Notice 1, 2, 3, 1, 2, 3. This is oxidized and cleaved right here. There's 2 of them because this side is the same as this side.